minus y squared. And then we have 1 divided by y to the 1/4 dy. All right. How should we start this off, guys? Yep, we split it up first, right? So we're going to have our first integral, and we're going to have that 2 over that root 1 minus y squared dy minus the integral of 1 over, let's just go ahead and rewrite that as y to the negative 1/4. Y to the negative 1/4 dy. I did that because it'll be a lot easier to use our I guess, reverse power rule, or power rule, whatever you want to call it, whenever we solve for that integral. Then we could also just bring this 2 on the outside, right? You don't have to, but it's there, right? Then we just have to have 1 on the inside. All right, so we have that ugly root 1 minus y squared, but luckily we have an antiderivative that we've memorized, or we should have memorized. Does anyone remember? Yeah, our arcsine. So we're going to have 2 arcsine y. And there's nothing being multiplied by this y. So we're just going to have this implied over root 1, which is just 1. So that doesn't really matter. And then what rule are we going to have to use for our next integral? Yeah, power rule. Yeah, our n+1 rule, right? So we're going to add 1 to our exponent. So 4 over 4 plus negative 1/4 is going to be 3/4, right? And then we divide by 3/4. So we're going to have 1 over 3/4 times y to the 3/4. Sorry, y to the 3/4. And then we're going to have our plus c. Now we just got to clean this up a little bit. Keep, change, flip that fraction. So we have 4/3 y to the 3/4 plus c. A lot of these beginning, how did I get the 3/4? So we have this exponent right here, right? And we use our rule of x to the n dx is going to be equal to 1 over n+1 x to the n+1. So if our n is equal to negative 1/4, our n+1 is going to equal 1 minus 1/4. We can rewrite 1 as 4 over 4. So we have 4 over 4 minus 1/4. And then that gives us our 3/4. And then we have to divide this number by 1 because of that rule up there. So that's how we end up with that 1 divided by 3/4. All right. The next 2 I'm going to throw at you guys are going to be a little tricky. Or I feel like they might trip some people up. They're not too bad, but they might trip some people up. So this one is just going to be 3x dx. I chose this one specifically because of the root 3. I wanted to see what you guys would do in that situation. So what's your first instinct when you see this integral? Yeah, I mean, we can't really take away the square root, but we can move out the 3. That's kind of what I was looking for. And then we can raise it to the 1/2 power. Let's just see what that does. Let's see if that does anything, right? So this is going to equal 3x to the 3 to the 1/2 power. Does that look any better? We are going to use our 1 over n plus 1 rule. Let's just see what happens, right? So if we add 1 to our exponent, right, what are we going to get? It's not a trick question, I promise. Yeah, it's just going to be root 3 plus 1, right? Right, so we're going to have this 3 over root 3 plus 1. And then our exponent's still going to be root 3 plus 1, right? So x is the root 3 plus 1. You can do this, but in this scenario, that's a really good thing to think, because we do that so often with our x's, right? But in this situation, it really didn't help us that much, but it's still good to try. It's still really good to try that stuff. Yeah, don't be scared to do stuff like that and see if it helps you. Yeah, this one really isn't that bad, but I know, like, whenever I see a root and an exponent, I think, oh my gosh, that just looks weird. I don't want to deal with it. But this is exactly the same rule that we use with our reverse power rule. Yeah, that's specifically why I chose it, because especially in a test setting, I feel like that's something Dr. Noring might do. So just be on the lookout for that. If it's just a number, if it's a variable raised to any number, you can use power rule, right? Even if that root 3 was like a natural log of 2, we would do the same thing, right? Like this is just not from the book, but as an example, if we have the integral x to the natural log of 2 dx, we would still do that 1 over natural log of 2 plus 1 times x to the natural log of 2 plus 1 plus c. So it really doesn't matter, or if it was like x to the e without any other variable, right? It would be the same thing. It can just be any constant. This next one, though, is actually tricky. And it probably won't be on the test, but just in case he puts something like this on the test, I did want to bring it up. And that's this one. It's number 65. And it's the integral of 1 plus tangent squared. I think they use theta. Tangent squared theta. D theta. And if you notice, tangent squared theta isn't one of our memorized derivative rules, right? But you do know something that will help us. Or you should know something that will help us. Yeah, that's exactly right. Remember those Pythagorean identities that we talked about, like, whenever we had that trig review, like, the beginning of the semester? R1 plus tangent squared theta is equal to secant squared theta. And I think I told you guys you should have all the Pythagorean identities memorized. Like if he gives you a sine squared theta plus cosine squared theta equals 1. And then the other one was, sorry, I have to do it because I actually don't even have them memorized. I have to divide by sine, yeah. Oh, it's going to be cotangent. So it's going to be 1 plus cotangent squared theta is equal to cosecant squared theta. Like I said, the only one I actually have memorized is this one, because I just divide it in my head whenever I think about it. But yeah, just know these in case he puts something like that on the first integral. I think there's only one, and I don't expect him to, but I did want to bring that up because I think it's interesting, and I always really like using these trig identities. But yeah, like Samantha said, that integral is going to be equal to secant squared theta d theta by our trig identities. And we know the derivative, or we know the antiderivative of secant squared theta, right? So what's that? Yeah, it's just going to be our tangent, right? It's going to be tangent theta plus c. All right. Let's do one or two more, and then yeah, that's the huge hurdle I feel like you have to get over with integrals is they look really scary until you either simplify them or just remember your derivative rules or antiderivative rules. And then it's like, oh, this isn't so bad anymore once you make it look less scary. The big thing with integrals is simplifying as much as possible. No problem, Samantha. Thanks for coming. I'm going to send the attendance link one more time. And I do have one more, but I kind of want to just make one up that I didn't find on there because it's one that I didn't see any examples of. So how would you find x squared? So let's see. Sin x squared minus 1. How do we solve this one? What would our first step be? I'll do this one and then I'll go into doing 11.2 and 11.3. I guess I'll ask how many of you guys want that, but how would we start this one? Yeah, we pull out the 4. So then we have 1 over x root 16x squared minus 1 dx. Yeah, I'm gonna do 11.3 again. Those other two I did the other day were the only ones I made up. But I mean, I can go over them again if you want that. But I don't have any additional problems other than that. My suggestion, if you need more practice with that, is to just Just, you can literally make them up yourself. Like, just make some up that you think will be hard, and then do the computations yourself. Because, I mean, that's exactly what I did to make up those problems. So I guess in this one, this is one of our memorized, right? And if you notice, we have this constant right here, right? This constant is going to be our a squared. So our a squared is equal to 16. So what's our a going to be equal to?
4.
Yeah, our a is just going to be 4. Right? So we know what's the antiderivative of this now that we know that our a is 4.
1 over 4.
It's one of our memorized ones. Yeah, it's going to be arcsecant 4x. That's exactly right. Plus c. All right, is there any questions about any of the derivative rules? Because I'm going to move into 11.2. Or how many of you guys are here for 11.2 and 11.3? I don't know how many of you guys were here. You're here? Okay. I figured at least one person would be that can't attend on Tuesday. 11.2 is hard. Okay, I'm going to go over it and hopefully make it super easy for you. All right, so let's do 11.2. All right, so they want us to find y particular for this derivative. So they give us a derivative dy dx, and it's x to the 1/3 plus x root x minus 2. Right, and they give us the initial values. X is equal to 1 and y is equal to 2. Right, so in every initial value problem, they're going to give you these starting values, so you don't have to worry about them. They give these to you. And they also give you a derivative. And the goal is to find y particular, which is, it's more of a differential equations term that you'll learn if you take ODE. But you don't even really have to know what that is. Basically, it's just finding the particular solution for those coordinates, right? What is our antiderivative c value going to be at those specific coordinates, right? So the first thing we have to do is just take its antiderivative. They give us the derivative, we need to find the antiderivative. So our step 1 is just to find the antiderivative of whatever derivative they give you, right? So this is our derivative. We're just going to slap this into an integral and solve it, right? So, and that's actually going to be what is known as our y general, or yg. It's the general form, meaning that we are just going to have a c in there somewhere. All right, so inside this integral, we have x to the 1/3, x times root x minus 2 dx. So the first thing I would do is I would split up these integrals, right? It'll help you not make a mistake anywhere. You can keep it as one. But I would split them up if that's how you've been doing them. So we're going to have the integral x to the 1/3 dx plus the integral, and then we see we have this, before I finish this integral, we see we have this x times x to the 1/2, or x, or root x. A lot of times we like to rewrite those roots as 1/2 powers. So I guess let's just do that first, and then we can combine them in the next step. And then we have plus the integral of -2 dx. Now if you remember our algebra rule, x to the a times x to the b is equal to x to the a plus b. So we're going to add this implied 1 power that's right there with that 1/2. So we're going to have that y general. And then I guess we can go ahead and let's do that all in the same step. I'm just going to leave that integral the same for right now. And then I'm going to combine those two x's to get x to the 3/2 dx. 1 plus 1/2 is 3/2. And then we have this minus the integral of 2 dx. And then once we've simplified to this point, once, this all looks doable antiderivatives for us, we can now apply those memorization tools that we have. And so what's our antiderivative of x to the 1/3 going to be? I guess, yeah. Well, we're going to add that 4/3, or we're going to add 1 to that 1/3 to get 4/3, right? And then, so we're going to have that 1 divided by 4/3. And then it's going to be x to the 4/3. I'm not really sure what you typed it in. I'm not sure if you made a mistake somewhere in there. Oh, yeah, I see. Okay. All right, and then for our second one, we're going to do the same thing. So what's the antiderivative for our second one? Yeah, we're just going to add 1. So it's going to be 1 divided by 5/2. And then it's going to be x raised to the 5/2. And then minus, and then we know just for any constant, we're just going to slap a variable on there whenever we take its antiderivative. And then we can't forget our plus c is the very important part. And then we're just going to clean this up a little bit before going to the next step. So we're going to have 2/5 x to the 5/2 minus 2x plus c. All right, so this is our y general, and it's considered our y general because we don't know what our c is. C could be anything. And then once you have the antiderivative, or this y general, because this y general is just the antiderivative, our step 2 is to plug in those values that they gave us. They gave us x equals 1 and then y is equal to 2. So that means right here where y is, we're going to plug in this 2. And then everywhere we see an x, we're going to plug in that 1. Okay. So we're going to have 2 is equal to 3/4, 1 to the 4/3, plus 2/5, 1 to the 5/2, minus 2 times 1 plus c. Then we just have to simplify. 2 is equal to 3/4 plus 2/5 minus 2 plus c. And then we get 2 plus 2 is 4. So we're going to have 4 minus 3/4 minus 2/5 is equal to c. And at this point, you can just plug that in your calculator using your fraction button, right? And you should get c is equal to 57/20. And now we're almost done. That's not our final answer because we're looking for y particular, right? Our step 3 is just to plug in c. That's literally all you have to do is just plug in c, and that's your y particular. Right, so we have our y general. Our y particular is going to be that same derivative or antiderivative but with that C constant at the very end. It was minus 2x. And then we're going to have plus 57 over 20. We brought the 2 to the left, right? We added 2 to both sides. And subtract. I think the other day in the other session, I mean, I had this exact same thing, but I rewrote C first. Yeah. If you do these 3 steps, yeah, I did look at the textbook. The textbook does explain it kind of weirdly, Abby. I agree with you. But if you do it in these 3 steps, you're gonna get it every time. So if you've been practicing antiderivatives and you just know those last 2 steps, then you should be able to solve it. Any questions on this one before I move on to 11.3? Yeah, no problem. I mean, I did say I was going to go over it, I think, in the group me, because I think a couple people asked, not just you. Yeah, now we can go over 11.3. Alright, so 11.3, they want us to find the sum of these summations. I don't know if these are technically Riemann sums or not, or if they're just summations. So I don't know if